I'm Jeff Mainland, and I'll be talking about metaprogramming with combinators. This is joint work with my former graduate student Mashid, who received her PhD a few weeks ago and is now working for Intel. I'd also like to acknowledge and thank the National Science Foundation for supporting this research. What is metaprogramming with combinators? I'll be advocating for a technique where programmers write lightweight code generation abstractions that provide a thin veneer over direct manipulation of concrete syntax. A key word here is concrete. There are several pros and cons to this approach. I'll highlight one of each. On the one hand, if we're directly generating code, we have more control over performance. On the other hand, direct manipulation of object programs is a real pain. At a certain point, we might as well skip the metaprogramming and program generation and just write the code directly ourselves. This approach is made more palatable by the combination of code-generating combinators and quasiquotation. Quasiquotation is a feature built into GHC that allows us to use concrete syntax to write object language terms. For example, if I were writing a program that generated C, C would be the object language, and by using quasiquotation, I could write C concrete syntax embedded in my Haskell code generator. This is much easier than writing C abstract syntax using deeply nested data constructor applications. The setting for the rest of this talk will be hardware generation, although the techniques I describe could be applied to any code generator. Our efforts grew out of a desire to generate hardware, where we found control over performance to be particularly important for reasons that I'll describe shortly. Our meta language is Haskell, that is, we'll be writing code generators in Haskell. We use Haskell because it has support for quasiquotation. Our object language is VHDL. VHDL is one of the two standard low-level languages for describing hardware circuits. If you care to know why we chose VHDL instead of Verilog, please ask me during the Q&A session. What we really care about is being able to build powerful new abstractions that we could not build directly in VHDL or Verilog, with minimal performance overhead relative to handwritten code. The primary metrics we care about are hardware resource utilization. We want to minimize the number of hardware resources our circuit requires, clock rate, because we want to run our circuits as fast as possible, and programmer effort, which we want to minimize. I hope to give you some insight into some of the challenges inherent in hardware design, especially if you don't have any hardware experience. A pipeline is a standard way to organize computation in hardware. Each stage in a pipeline performs a computation on every clock cycle. The stages all run concurrently. A stage takes its input from an upstream producer, performs a computation, and sends the result of the computation to its downstream consumer. We'll assume a single global clock, which is typical. Every stage consists of some combinational logic, which computes a pure function of its input, as well as registers, which store their input to their internal state on each clock tick and continuously output their current state. Wires between different components carry continuous signals. The clock is what determines progress via changes in register state. Breaking up a computation into multiple stages is necessary because signal propagation isn't instantaneous. The hardware that implements combinational logic takes some amount of time to settle into a stable state after its input signals change. A given stage may not always be able to process an item in a single clock cycle. It's also possible that pipeline input is not available on every clock cycle, or that the pipeline's consumer cannot accept a new output on every clock cycle. To account for this, pipelines use a handshake protocol for flow control. There are many different handshake protocols. Unfortunately, we can't build abstractions in VHDL or Verilog that abstract over the handshake protocol by separating out the pure combinational computation. However, we can build this kind of abstraction in a functional language like Haskell. Why is performance especially important in the hardware domain? It's because the global clock can only run as fast as the slowest stage. Local performance has global implications. A single slow stage can tank global performance in a hardware circuit. If we want to build a pipeline abstraction in Haskell, we already have many circuit generation tools at our disposal. Two that exemplify different approaches to code generation are Clash and Kansas Lava. Clash compiles Haskell to hardware via GHC's core language. Programmers can write standard Haskell to describe a circuit, but not all Haskell constructs can be synthesized as hardware. For example, recursive functions are not synthesizable. Kansas Lava is a classic Haskell embedded DSL that grew out of decades of work on the Lava language. It improves on past versions in many ways, including by making use of modern Haskell features like size types. These are both excellent tools, so why bother with a new approach? We want to know what costs these systems impose. Before we pick a tool, let's do some benchmarking. We'll implement a simple pipeline in all systems and look at the metrics we care about: resource utilization, clock speed, and programmer effort. Our running example will be a multi-stage incrementer, a pipeline consisting of in stages where each stage adds 1 to its input. This pipeline performs a minimal but non-zero amount of computation at each stage, which makes it useful for measuring the overhead of our pipeline abstraction. Here's the pipeline implemented using the Metaprogramming with Combinators approach. The Clash and Kansas Lava implementations also only take a few lines of code. There are 2 versions of the pipeline. The first version is a serial pipeline. It iterates the addition function 16 times using a single pipeline stage. This uses a minimal amount of hardware, but it also limits the steady-state throughput of the pipeline to 1 item every 16 clock cycles. The parallel version iterates the addition function across 16 separate pipeline stages. This uses more hardware, but it means the steady-state throughput of the pipeline will be 1 item per clock cycle. Both pipelines have a latency of 16 clock cycles. The SIDER and PIDER functions are both members of the pipeline type class. They allow programmers to trade hardware resource utilization for throughput by changing only the combinator used. It's also possible to have even more fine-grained control over this trade-off by performing multiple computations per stage instead of limiting the choices to 1 computation per stage, as in the parallel case, or all computations in a single stage, as in the serial case. Several other pipeline operations are described in the paper. I said earlier that I was advocating for an approach that uses direct manipulation of VHDL, and yet here I've written my pipeline using a Haskell function. You should rightfully be suspicious. We'll come back to this point in a moment. These pipeline combinators also allow pre- and post computations to be specified, which are folded into the first and last pipeline stages, respectively. We don't use them here, so they're both the identity function. We'll see the VX type again momentarily. This is the type of VHDL expressions. The UQ type is the type of unsigned fixed point numbers. Here we're using fixed point numbers with 16 integral bits and 0 fractional bits. The pipeline type is indexed by the type of its input and the type of its output. Our pipelines both take an unsigned 16-bit integer as input and produce an unsigned 16-bit integer as output. We actually implemented our pipeline abstraction 4 ways, and the performance results of the implementations are shown here. The 4th implementation made use of Kansas Lava's embedded RTL DSL for describing stateful computations directly. We found we were able to improve performance in some cases by making use of the RTL DSL, so we also used it to try to implement the pipeline abstraction. The table shows metrics for the serial and parallel versions of the pipelines across all 4 implementations as compiled for a Xilinx FPGA. The LUT and flip-flop columns, labeled LUT and FF respectively, show the number of each resource used for the FPGA implementation. The Fmax column shows the maximum frequency at which the circuit can be run. The first thing to note is that Kansas Lava imposed a substantial overhead for stateful computation even when we used its RTL DSL. Except for the Metaprogramming with Combinators implementation, the parallel pipeline was always substantially slower than the serial pipeline. In all cases, the Metaprogramming with Combinators implementation had the lowest resource utilization and highest clock rate. Why? Because we could tailor the generated VHDL precisely to the handshake protocol. There was no extra cruft produced as a side effect of the code generation process. I'll make a few observations and raise 2 questions that I want to answer during the rest of this talk. First, control over generated code equals control over performance. The next observation is that combinational circuits are a great fit for functional languages. The problem is state, or registers. We saw this over and over again when we used these systems to build hardware. One of the big benefits of systems like Kansas Lava and Clash is that the same program can be both run as a purely Haskell program and used to generate code. Does using the Metaprogramming with Combinators approach lose that benefit? In the benchmarks I've presented, I ignored one of the metrics I said I cared about: programmer effort. Maybe I'm able to write more performance circuits using this new approach, but how much more difficult have I made my job? I want to take on the first question now. If I'm essentially directly generating VHDL, how can I recover the ability to run my code generator as a pure Haskell program for the purpose of testing? The serial version of the multi-stage incrementer pipeline gives us a strong hint. First, we use an embedded DSL to write combinational circuits instead of writing VHDL directly. The mapping to VHDL is usually so direct for this type of circuit that we don't lose any control over the generated code. However, we could always drop down to VHDL if we were willing to give up on running our circuit as a Haskell program in exchange for extra control. We then capture stateful abstractions as type classes and write different instances for Haskell and hardware generation. The paper describes an instance of the pipeline type class that builds runnable Haskell pipelines. There's one more key element to recovering the ability to interpret circuits as Haskell programs, the VExp data type. The VExp data type, which represents VHDL terms that are built to express circuit functionality, uses a mixed shallow and deep embedding. The vconst data constructor builds a shallowly embedded term using a Haskell value. The toExp type class classifies types whose values can be converted to a VHDL term. The VExp data constructor, on the other hand, represents deeply embedded terms, that is, VHDL code fragments. We can always convert a shallowly embedded term into a deeply embedded term, but not vice versa. If we maintain the invariant that computations using only shallowly embedded terms will produce only shallowly embedded terms, then we can recover the ability to interpret a circuit as a Haskell program by injecting Haskell values using the shallow embedding, and then projecting out the resulting shallowly embedded values. Let's briefly dig into the implementation of the parallel pipeline combinator for the pipeline instance that generates VHDL. This combinator runs in a code-generating monad whose operations are captured by the monad.cg type class. These operations include things like gensim and the collection of generated code. Here we see a quasiquote being used to generate a VHDL unit. The V unit name at the beginning of the brackets specifies the syntactic category of the quasiquote. It is part of the VHDL quasiquotation library we wrote as part of this work. The bolded sections that start with $signs are antiquotes. They're Haskell expressions whose values will be spliced into the quasiquote. The Haskell variable entity is an identifier that will be used as the name of the VHDL entity being generated. The Haskell variables in_decals and out_decals are lists of interface declarations that specify the VHDL unit's input and output signals, respectively. The append operation, a member of the monad.cg type class, collects generated code. This is the main code-generating portion of the combinator. Quasiquotation is used extensively to generate VHDL code fragments. There are a number of combinators used, like with architecture, with process, and on rising edge, that provide scoped code generation constructs. These scoped code generation constructs map directly to VHDL, but they allow us to write code generators compositionally in a way that is not possible using quasiquotation alone. We've overloaded when and used GHC's rebindable syntax feature to overload if. The overloaded constructs can now take a VHDL Boolean value as a conditional, in which case they generate code. Although quasiquotation is inherently unhygienic, we can recover hygiene through the use of combinators. The 4S combinator is one such example. It gensims a loop variable, which is passed to its continuation. The continuation generates code for the body of the loop, and the 4S combinator uses this loop body to in turn generate a VHDL for statement. We've now seen all the building blocks of the metaprogramming with combinators approach, a mixed shallow-deep embedding and a library of combinators built using quasiquotation. We've not yet seen the final metric I stated was of interest at the beginning of the talk, programmer effort. This table shows the lines of code required to implement the serial and parallel pipeline combinators using each approach. Metaprogramming with combinators takes about twice as much code in this case, which is consistent with our general experience. The implementations aren't exactly equivalent. The metaprogramming with combinators implementation is slightly more general, but that extra generality doesn't fully account for the increased programmer effort. The pipeline type class is the kind of abstraction we expect programmers to be able to build themselves using the underlying code generation monad and VHDL quasiquotation library we've developed. There's much more in the paper. I hope I've enticed you to read it, and I look forward to your questions during the Q&A part of this session.